So the last two important topics that are left out in this chapter are, we need to calculate. I'm just going to teach you the method to calculate. 1 minute. Time period of the first wire we are going to see for a simple pendulum, and the second we are going to see for a spring and a block system. Okay. So these are the two time periods that we are going to derive. That is for objects which are in oscillation. Okay. Now, see, there are certain steps to be followed. So steps that I'm going to tell you are not only applicable for these two concepts, it is applicable for any problem you do in simple pendulum. Okay. Steps to be followed, any problem where you need to calculate time period. Steps to be followed to solve problems in SH. First is draw a free body diagram. Second, once you draw the free body diagram, find the unbalanced force responsible for the system to come back to its mean position. Okay. Third, equate the unbalanced force. The unbalanced force that I'm trying to talk here is nothing but the restoring force. Unbalanced force can also be called as restoring force. Equate the restoring force to M into A. Okay. Once you do that, from step 3, obtain expression for acceleration in terms of displacement. Obtain the expression for acceleration in terms of displacement. Fifth step is compare the expression obtained in fourth step with A is equal to minus omega square x. Okay. Compare the expression obtained in step number 4 with A is equal to minus omega square x, or if at all you're talking about rotation, you'll see this kind of expression also. Alpha is equal to minus omega square theta, where alpha stands for angular acceleration and theta stands for angular displacement. Okay. Alpha is equal to minus omega square theta. This is also applicable. It will be dependent on the problem, whether you're trying to solve a problem in translatory motion or rotation motion. If you're doing a problem based on translatory, you will get A is equal to minus omega square x. If you're solving a problem based on rotational, you will get minus omega square theta.
So you can say what theta stands for?
Angular displacement. Theta is angular displacement. Okay. Sixth step. Obtain the expression for omega from above step. And the last step is write omega is equal to 2 pi by t and find t is equal to what? And just find t, that's it. No question mark. Just find t. See, these are the steps you need to follow for any problem, irrespective of its chapter. For example, if there is a problem which is based on fluid dynamics and it is in simple harmonic motion, if you follow these 7 steps, you will get the answer. If it is from some other, if let's say it is from gravitation, it is based on, you need to calculate time period. Follow 7 steps, you will get the answer. Okay. This you will not find it in book. Please make a note. So once you are done, I'll proceed. Shall I proceed?
Yes, sir.
Okay. Listen. This is easier. Okay. Right. Now let's see. So we'll calculate the time period of a simple pendulum. Let's see how to do. So let's say you have a simple pendulum which is suspended with the help of a string of length L. Let's say it is displaced to this point where it is making an angle theta with the vertical, and then it is released. In the sense, the force that you have applied is released on it. Now, what are all the forces that are going to act on the bob at point A?
Restoring force, sir.
Yes. One is mg. And if this is theta, this is also theta. Then this will be mg cos theta, and this will be mg sin theta. Okay. So here, tell me, is the pendulum in a translatory motion or a kind of rotation motion? Is the bob rotating or is it in translatory motion? So when I say translatory, it should be in a straight line path.
Rotational, sir.
It is rotational motion, right? And remember this point, let me call it as P. Now observe, guys. It is due to whom? It is due to the mg sin theta that the bob is actually coming back to its original position. Correct? Now my question is, so let's say, let's verify whether we have followed the steps. I've drawn the free body diagram. I found out what is the unbalanced force which is responsible for the object to come back.
So how did you find the unbalanced force?
Because I showed no. Which direction is the, see, practically when you see in which direction is the bob going to come? Towards its mean position. From A to O, no. Which force is going to pull the object from A to O? Obviously, it is mg sine theta. So that is the unbalanced force.
Restoring force is okay, sir.
Restoring force is unbalanced force. That's what I wrote here, no?
Okay, sir.
Okay. Equate the unbalanced force to MA, or please add another point. Unbalanced torque to I alpha. Please make a note. I forgot to write this. If you have unbalanced force, equate it to MA. If you have an unbalanced torque, equate it to I alpha, because torque is equal to I alpha. I explained it in the 7th chapter. Right. From step 3, obtain the expression for A. I'll write another point, or alpha, in terms of displacement or theta. Please make note. When I say displacement in terms of x, when I say in terms of theta, it is in terms of angular displacement. So I'm repeating the step. Please add this point. From step number 3, obtain the expression for a acceleration or angular acceleration in terms of displacement or angular displacement. Shall I proceed, guys? Now see.
So 1 minute, could you show it again?
Yeah, sure. In terms of displacement, in the bracket you can write it as x. Displacement is x, or theta. Theta is angular displacement.
Okay, sir.
Okay. So remaining steps are right. There is nothing else to add. Now, what is the torque? What is the torque experienced by the bob about point O? What is the torque experienced by the bob about point O? That's this is the axis of rotation about which it is revolving. We know a formula. Torque is equal to, in terms of magnitude, force into perpendicular distance. You know this, right? Torque is equal to force into perpendicular distance. To restore the object, which force is trying to restore the object?
mg sin theta.
Mg sin theta multiplied with, remember, mg sin theta and L are perpendicular because,
Sir, your voice is low, sir.
okay,
Your voice is low.
so remember, mg sin theta will be perpendicular to length because mg sin theta and mg cos theta are rectangular components. They are perpendicular components, right? When mg sin theta is along mg cos theta is along the length, then mg sin theta will be perpendicular to length. So what is going to be the perpendicular distance from mg sin theta to point P? It is AP. That is nothing but mg sin theta multiplied with L. Guys, am I clear?
Yes, sir.
Okay. So this is the restoring torque that is acting on this bob. That is mg sine theta into L. Okay. Let me call this as equation number 1. I'll make it. Let this be equation number 1. For theta being very small, okay, whenever the value of theta, where theta is measured in radians, whenever theta is very small, then an important point to be observed is sine theta can be approximated to tan theta, that can be approximated to theta. This comes from the idea of limits. Okay, whenever theta is very small, sine theta and tan theta are almost equal, because what is sine 0? Sine 0 is 0, tan 0 is 0. Sine 0.00001 radian will be approximately equal to 0.0001 radian only. It is that small value. Okay. So whenever the value of theta is small, sine theta is approximated to tan theta is approximated to theta. Okay. So what I'm going to do in this case is that implies torque is equal to mg into theta into L, because here we need to consider theta to be very small. This is one approximation that we are doing. Okay. So this is how we are obtaining. So what is the approximation if they ask? You need to say that the value of theta is very small. The angle made by the pendulum with the vertical is small. Is it clear till this step, guys?
Yes, sir.
Okay. Okay. So what is that you got? Torque is equal to mgl into theta. Now see, since it's a restoring torque, torque will be equal to minus mgl into theta. I hope you understood why I wrote that minus. The negative sign indicates it's a restoring torque. Okay. So torque is equal to minus mgl into theta. Let me call this as equation number 2. Once you find, listen, let me show, then you can copy it. Okay, concentrate. Okay. Once you find the restoring torque, what are we supposed to do? You need to equate it to I alpha. So we know that torque is equal to I alpha, which implies minus mgl into theta is equal to I into alpha. But what is the value of I in this case? I is moment of inertia. So what is the formula for moment of inertia of a particle? Moment of inertia of a particle is equal to mass into distance square. So the mass is here, and how much is the distance from A to P?
L, sir.
It is m into L square. Let us see. Let us see 3, let us see 4. Take 4 and substitute it here. What will you get? You will get minus mgl into theta is equal to ml square into alpha. Correct? M and M are gone, L and L are gone, which implies alpha is equal to how much force? Minus G divided by L into theta. Let this be equation number 5. There is the most important step in the derivation. So alpha is equal to minus G by L into theta. Please make a note. See, since I'm explaining this, the derivation is going big. Actually, if you see, it is only 5 to 6 steps. Okay. After I complete this, I'll give you a simplified version of how you can practice. So alpha is equal to minus G by L into theta. Correct?
Yes, sir.
So, shall I proceed?
Yes, sir.
Okay. So after you obtain alpha, what are you supposed to compare it with? Comparing alpha with minus omega square theta, we get minus G by L into theta is equal to minus omega square theta. Correct? Minus minus are gone, theta is gone. So omega square will be equal to G by L, which implies omega is equal to root of G by L. From this we can write, what is omega, guys? 2 pi by T is equal to root of G by L. So what will be the value of time period? You remember we saw this formula in the first chapter itself. We calculated the error in the time period of simple pendulum. They would have told the time period of a simple pendulum is given as 2 pi root of L divided by G. Clear?
Yes, sir.
Let me know once you're done.
So could you go to the starting of the derivation once, where the torque came in? Yes, sir. Just a minute. So could you explain again why theta is very small, sir?
That is how we take it. This formula is applicable only when the angle is small.
We are considering it like that.
We are considering. It is not
Okay.
necessary that theta has to be small. You can pull it to whatever distance and you can do it. See, that is how the derivation is actually, okay? But if you do it on a practical basis and see how much ever angle you try to pull it to, because the final expression is independent of angle, right? Nowhere you are sin theta or cos theta. So how much ever angle you try to pull it and release, no, there will be a small variation, microsecond variation in terms of the values. See, have you done this experiment? Any idea how you do it? In the lab, you'll have a stopwatch. They'll give you a simple pendulum of, let's say you take off two different lengths. If the length is changing, time period will definitely change. Okay. Let's say you pull it to this distance and leave it. Once you start the stopwatch, you calculate, let's say 10 oscillations. You will calculate the total time for 10 oscillations. And if you divide it with, and you will get a time, let's say you're getting it as 2.32 seconds, something like that. Okay. It's very fast actually. If you divide it with 10, you will get it as 0.232 seconds for one oscillation. That is the time period of one oscillation. So there you are calculating it practically using a stopwatch. How will you verify whether that value is right or wrong? By substituting it in this formula. You will calculate the length of the thread that you have in your hand. You will substitute the value of G, and when you multiply it with 2 pi, the practical answer, that is this stopwatch answer, should match with this theoretical answer. Okay.
Sir.
But to be very precise, there will be a slight variation. Definitely it will appear. It might be due to any error, because there is definitely air resistance that is going to exist depending on the lab conditions you're doing. Suppose you switch on the fan and do, the speed might vary. Okay, if you don't switch it on, it will be something else. Okay, but the answer should be close by. Every experiment will have an error.
Okay.
So to answer your question, in this derivation, we are assuming theta to be small.
Okay, sir. Thank you, sir.
Okay, so I'll tell you how you can do it in few steps. You can practice it like this. So once you complete the free body diagram, then torque acting about point P is mgl sine theta. You will write that force into perpendicular distance, right? Force is mg sine theta, and the perpendicular distance is L. Okay. Secondly, you will write the restoring torque as minus mgl sine theta. And third step, you will write, since theta is small, torque acting about point P is minus mgl into theta. Okay. And torque is equal to I alpha and I is equal to ml square. Okay. So minus mgl into theta will be equal to ml square into alpha. L and L will get cancelled. M and M will get cancelled. Alpha will be minus g by L into theta. So comparing this with minus omega square theta, you will get omega is equal to root of g by L. T will be equal to 2 pi root of L by g. So these are the steps. So when you're practicing, you need not write everything, okay? See, but when you write it in the exam, this is how you need to do. You need to write why that particular expression has come. But when you're practicing it for your purpose, you can actually do it like this, so that you will remember the intermediate steps. Now, if you practice it like this, there will be a point where you can skip few steps also and obtain the final expression. Then you will get used to it. Okay.